Thank you, Mike. I think Egon would be actually delighted to be here today and see so many talks that relates to his work. But also Bill mentioned that Egon was a very flexible intellect and was interested in lots of things and particular interest in practical things. So as I thought about my talk, my own career kind of drifted a little bit from hyperplanes and cutting planes. And so I want to talk a little about something that I think is really practical and doable, and relate this to what OR can contribute. So I'm going to talk about traffic congestion and how we can use OR to eliminate it. It's a little different talk in the sense that I'm not claiming results or theoretical theorems, etc. It's an approach. As I said, I think it's doable. I can see a clear path to implementing this in our lifetime, so to speak, but there are so many OR problems or parameters and research questions that potentially this opens. So everybody who wants to grab this and run with it, you're just welcome, of course. Oh, that's not it. This is, well, so I'm not going to spend a lot of time talking about the impact of traffic congestions. You all know about this from practical, personal experience of getting stuck in traffic, and people are pretty good at throwing numbers about the billions of dollars that are being spent in traffic. A little bit my own interest in this started about 2 years ago. I was serving as a consultant to the provost of the University of Chicago and traveling from University of Chicago to the airport on a routine basis. And those of you that are from that area know that this is a major problem. And every time I was there, at the end of the day, stuck in traffic for an hour and a half and thinking, boy, I could have 2 or 3 or more meetings that I could have done. So I started thinking about what do we know about it and what people plan to do about it. And came about the many papers like this. This is a typical kind of thing. It's a white paper. In fact, the RAND one is almost a book. It talks about Los Angeles, of course, is notorious for traffic jams. And it really is a systematic analysis of all the different approaches that people come up with to tackle the problem of congestion. At the end, it identifies 13 strategies that are applicable, in their opinion, to that particular situation. Nothing there is about networks, about capacities, about bottlenecks, etc. In fact, this is the major conclusion to put in top. Any approach that does not include pricing strategies will not achieve lasting reduction in traffic congestion. So they are talking really about economic solutions to it, which is, of course, the original of this is what's called now congestion pricing by Vickrey. And Vickrey's idea was that when you enter a congested line, you're creating externalities on the other people. And if we can charge you for those congestions, we will get to some kind of economic optimum. That's the thing. Now, I need to tell you this: when you talk today about promise and about what possibly can do, this congestion pricing is perhaps the one that comes every time. I frankly don't think it will solve the problem. And it's an extremely unpopular thing because really the bargain that you are doing with the audience, now I'm stuck in traffic and it's free, The solution will be I'll be stuck in traffic and pay. Really going about it through prices, I think, is maybe the wrong way. So in terms of contributions, I'm going to start at the end because I started thinking about it last year and then stumbled about a colleague, his name is Luricchio, who was the the transportation commissioners of New York City, and he's interested in that. We kind of came up with the same ideas, discovered each other over lunch, and then Zawei Zhang joined us with some kind of algorithmic work. But really, when we started digging the literature and people talk about what the solution that I outlined a little earlier in a simplistic fashion, I'm really talking about reservation system for traffic. So this was done by in Japan, in Tokyo, and actually the interesting thing about it is a survey that he asked whether people would be ready to register for traffic, and the surprising result was that 90% of the people say they would do that. And then a sequence of other people, including the last one that we have discovered, usually theoretical analysis of a simple solution. So let me talk to you about the end, because if I come up with a solution, you all say I'm crazy, as that's the result I get all the time. I want to talk about the impact of this. What am I trying to achieve? And I am going to talk about the first order effect, which I call the great bargain. The OR cannot eliminate traffic congestion in the sense that whenever you want to drive, I create a condition whenever you want to drive, you can drive and nobody will be in the way. That is actually not the right criteria to compare it. So what is the best world? What is the best achievable? And how close can we get to it? And that best thing involves a bargain. What am I asking you, the driver, and what am I giving you in return? That's really what I'm talking about. There are two second-order effects that I think I call them magnifiers. One is called the congestion paradox, and the other one is the effect is traffic disruption. What do I do when there is traffic accident, when there is a traffic construction, something goes on the road? This would be a question that everybody asks me when I present this thing. And I want to say that those two things, of course, exist. They only make this method, in my opinion, better. They are magnifiers of the benefit, and I'll really talk a little bit about this. But the major thing will be in terms of the first order effect of this, which is, okay. So let's just look a little bit about simplistic of the rush hour traffic buildup. I'm describing here the x-axis is time. This is traffic buildup, cumulative traffic buildup on a congestion system, let's say a highway or a bridge or something like that. And I put here in yellow, that is the capacity of that system. So you can see that before in the early time, traffic arrives less than capacity, and reach capacity, exceeds capacity, and come back. That's the standard trade-off like this. So if you look at this system, and you look not at when people decide to enter the system, but when people actually leave the system, which is what I call the output of the system, when people reach their destination. So this is a simple arc. People enter, you get this curve. So at first you see that maybe the distance here is 3 units of time. These people that came on this time are going to live here. People that came here are going to live here, etc. The difference on this axis between the two curves is the time people spend. The difference on the y-axis is how many people are stuck in traffic in this graph. You can see that once we reach capacity, then this line follows that line, and eventually they kind of they taper off. So if you, for instance, if you enter the system at unit 15, time unit 15, just have to go over there, and maybe you're leaving the system, I don't know, 30. You're in the system 15 units of time, and 3 of those units is really actual driving. The rest, you're driving all the time. But we can think about it as 3 units of driving and 12 units of waiting, all right? So what's the bargain? Why is this? Oh, I'm sorry. I kind of was preparing because tomorrow I need to get to the airport. So this is the, this is the 3 units of time. This is the time before rush hour to get from CMU to the airport, 22 minutes. And you can see as time moves that this is building 36 minutes, 54 minutes. I think it reaches all the way to an hour if you go to the rest. So I'm just, this kind of thing kind of illustrate what we're talking about here. Are you with me? All right. So what's the bargain? Propose that if you give up the right to enter the system anytime you want, give it to me, I'll get you into your destination at the same time that you would have gotten there, that you're getting there right now. Right? Are you with me? I'm going to ask you to stay at home, so to speak, a little later, leave when I'm telling you to leave. You will still get to your destination at the same time, but instead of getting stuck on the road, you'll be at your office, you'll be at your home, you'll be more productive time. That is what I call the great bug. Okay? And actually, a lot of what I'm discussing is how practical it is, how close we can get to this, and whether this is all doable. I think we can think about this happening every day now. I give up my right to go to the doctor anytime I want. And in return, I schedule and I arrive there and I don't wait. So this is the same thing. I think the new thing here is not new. The timing now is that we have the algorithmic, technological, and managerial capacity to have something like this in working. Yes?
It is applied in the airline industry. It is the ground holding policy.
In airlines do it all the time. Airlines do it. They don't let you take off if there is no position for you to land. It's conceptually not different than making reservation for a restaurant or for a play or whatever, right? The thing is that this was a little bit inconceivable, I think, 20 years ago, but now we have the algorithmic power and we have the technology. And I think that when we have automatic vehicles on the road, this is probably going to be the only way that cars are going to drive. You have to reserve. So the whole thing is, when you enter the system, you have reserved a pathway clear of any congestions all the way from here to destination. That's my plan, so to speak. All right? So let me talk about the two. So that's the first order effect. The second, those are the two second order effects. One is called the congestion paradox. The congestion paradox is something, it's an observation. I think many of you can probably relate to it. This, you can think about this is input intensity, traffic intensity, and on the outside, output intensity. If you have a simple capacitated system, the first model that we have is that more input gets you more output until you get to capacity, and then you're staying capacity, which is what I used in the previous example to drive. In reality, the observation is that we have something like that. The more, if the system gets congestion, not only are we stuck at capacity, but actually capacity is decreasing. If capacity is decreasing, that's actually going to be much better in my system, because if you look at this, this is the great bargain that we talked about before. This is this is the arrival time. This is when people leave now. This is when I promise them to leave. But if you have the paradox, actually, by staying at home until I tell you, you're going to get to your destination earlier, because we are going to operate the system at the true capacity and not at the reduced capacity that we had before. Right? The second point is about disruption. Of course, what do we do in case of disruption? I think this system is going to actually shine in the case of disruption, because if you look at disruption, this is the situation. So at some point, capacity, I just say, dropped to 0. So the arrival is still the same, but of course, departure is getting delayed. This is the system that one can get, but here is what I'm claiming, that in fact it will be even better, because when roads are congested and there is an accident, the time and the effort to clear the mess that's happening. You just think about the whole thing, about the police car honking and trying to get through congestions, etc. If the roads are clear, taking care of all of those interruptions will actually be faster. So you're gaining capacity that way. In other words, this system will work better, relative speaking, in disruption. It's not that one can say if there is disruption, we ignore it, it didn't occur, but the impact of it would be reduced with this system. All right, so I want to give you two simple examples for this before we talk about the main thing, which is a true reservation system for every road on for real transportation networks. After the game is over, so this is actually Disney World. But think about a concert, or think about a baseball game or whatever, and all those cars are in the parking lot. And at some point the game is over, and everybody is rushing to get out. And so what happens is a lot of people actually start thinking about going out before the game is over to beat the concert. But the end result is you are sitting in the parking lot, crawling at 0 miles per hour, trying to get your turn. So the idea is one can easily set a system when you enter this, when you buy a ticket, I not only give you your ticket, but I also give you a time for departure. And you can easily think about how this could work, say, in a baseball game, where we can easily arrange for some after-game activities. So, for instance, there may be food services, maybe there is a show, maybe there is something, and you may get a ticket, and the ticket tells you you are stay in your office, in your seat for another half an hour, and then you can exit the system. The point again is, I'm not making. It looks like a lot of people say, you are telling me to stay. I'm telling you to stay, but I'm going to get you out at the same time that you would go out anyhow. Instead of sitting in the parking lot, that's a hint for me. It's a hint? 4 minutes. Okay. Second example is I call bottleneck rest areas. We have rest areas in many places for rest, but I'm proposing of putting urban, or whenever this is feasible, this requires major investments. If, let's say, you enter New York and you're going through the Holland Tunnel or one of those tunnels, if in front of the tunnel there was a rest area like that, where you can come in and you can park your car and you do your email and you could do your phones and maybe you can do your shopping and maybe you can go to the restroom and maybe you can do some, grab a cup of coffee. And the whole thing is when you enter the system, you get a time and will tell you that you can leave that thing at a given time. And of course, the timing is according to the capacity. So in the tunnel itself, there is never congestion. There's another. Okay. what are the elements of a system like this? Is really a quasi or dynamic network flow system. We all know what a dynamic flow system is. It's a standard transportation system with travel time and distances, very similar to what Uber or any of those Google Map is using, et cetera. And then there will be a time grid. We are looking at a day and breaking it into intervals, say 15 minutes interval. We have to keep a database of every arc for every time slot. We need to know what is the capacity. I call capacities, in a second I'll explain. What is the already committed load on that road, on that thing. So I need to know maybe I can do 100 cars in that 15 minutes and already 60 are allocated, so I have 40 more. And at some point there will be an on-off switch where I say that road, that link is capacitated and I cannot allow any more cars to enter this road at that time. Why do I say capacities? Because I may decide to break a capacity of an arc into different categories. For instance, I may want to say X percentage of it is dedicated, say, to police or to other services. Some of it may be allocated to commercial, some to residential, some could be allocated to carpools, public. You can divide it in many ways and treat each one as a slice of its own. You can even leave some of it as free on a first-come, first-basis. So what is quasi? And this is, of course, this would give us some kind of, we all know this, how to handle dynamic networks. It's a layered network. I think that perhaps we can also use here something called quasi-dynamic. A dynamic network means that if I go from node 1 to node 2, and I want to go from node 2 to node 3, already the parameters of my time say it takes me a minute to get there, I have to look at the situation at that arc when I will arrive there. A quasi-network is when I ignore this. I just say this is the network at 8 o'clock or at 9 or at 8:15, etc. I'm not sure which one could be used. All of them are actually pretty easily handleable. I need some system for handling requests. People are going to request permission to enter the system. They will need to give me information about where they're going, some parameters of arrival and departure, some preferences if they want. And then one can think about how do we handle this? Do we handle it online, application by applications? There will be millions. Say 1 million people enter New York City every day, so or maybe batch them and handle that. And then one can even think about subscription system, which if you're a constant traveler, you have a subscription, you have your slot every day or something of that nature. We need to think about a reservation system, takes those requests and give you actual permission to go at a given point in time. This could be priorities. It could be based on price. I could be selling those spots, which I personally don't particularly like, but I think most politicians look at the cost, the revenue implication of this. It could be first come, first serve. It could be rotations. I think the issue with pricing, especially with a city like New York, where congestion pricing is extremely unpopular, is because this really magnifies economic differences in the cities. There are the vast differences in income in New York is such that you can easily get into prices that are zero for Wall Street, but are infinity for everybody else. And that's just not the right way to do it. So you can think about some kind of system. For instance, if you're driving to the city every day and on a subscription basis, I can give you 1 day a week, you get your number 1 priority, 1 day a week, you get number 2, and then the rest of the time, so you have a little bit more of a social justice element. All of these are irrelevant to the great bargain, but there are, I think, parameters of implementations. Now, the algorithms are very simple. This would be a shortest path if we are a dynamic shortest path or quasi-dynamic shortest path, or a maximum flow. I talked about interruption. I have one more slide. And so I'm thinking that you would have some application like this, and you maybe make a request, and you get the permission, or it could be something connected to the car. That's another parameter. Do we connect this to a person or to the car? Here are some of the options that we have. Do we do it for entire region, or let's say to bottlenecks, for instance, to a tunnel or to a region, entire day or peak hour, single-use subscription, the revenue source. There are two revenue sources here. One is you can sell the thing, or you can find people that, and then whether those permits are restricted to the person, whether you can pass them around, whether you can trade them. There are lots and lots of questions there, whether you can auction them, et cetera. So, and enforcement, how do you do the enforcement? So, just a point in terms of the great, the great bargain. Of course, we all know that the shifting bottleneck situation, and that you could not guarantee this in a complex network. You can guarantee this, but we have some results on some networks. For instance, if you have a network like this, which represents traffic into the city in the morning, then you actually could achieve this. Okay, sorry, thank you.
Fascinating stuff.